against software-defined networks. So I'll hand it over for your presentation. Mr. Bahashwan, you there?
Yes, I'm there. You hear me?
Yes, we can hear you now. Thank you.
Okay. Good morning, everyone, and thank you all for being here today at the MAN 58 Security Working Group. My name is Abdullah Ahmed. I appreciate the opportunity to present my work on high rate and low rate dataset-based DDoS attack against SDN, and share the insights and contribution I have gained through this process. Without any further delay, I'm going to start with the introduction. Nowadays, the traditional network suffering from many issues in terms of management, security, and other essential aspects. For this reason, new technology has shown up to enable higher management and giving more flexibility. This technology is known as software-defined networking controller. The SDN is a new networking architecture that separates the control plane and data plane. This innovative technology is designing for next generation networks that have been repeatedly highlighted with the OpenFlow protocol. The SDN is a central controller that manages the whole network flow with the minimum efforts, makes the network more scalable and agile. As can be seen, this figure illustrates the difference between the SDN network architecture and traditional network architecture. The SDN networking architecture consists of three layers. First, the application layer consists of application programs that are implemented over the control plane and communicating with the SDN controller through the northbound API interface. Second, the control layer that contains the SDN controller to rule the entire network functionality. This is the last data plane layer that consists of the SDN switches or devices that communicate with the SDN using southbound API interface. The SDN architecture became broadly adapted in new emerging technologies such as cloud computing, IoT technologies. However, several security challenges appear to disturb the SDN network normal operation. The SDN network has no security defense by default, which exposes the SDN controller to the most common attacks of these days, like high rate and low rate DDoS attacks. In recent years, there has been significant increase in the use of deep learning approaches to address the requirement for developing powerful detection systems. One significant advantage of deep learning over traditional machine learning is the superior performance in analyzing large-scale datasets. Additionally, deep learning has gained popularity in detecting SDN DDoS attacks flooding due to its ability to learn the complex patterns associated with these source attacks. This slide discusses the relevant works on deep learning-based approaches that utilizing for detecting SDN DDoS attacks. As presented in this table, these approaches having some limitations. One of these limitations, most of these approaches primarily focusing on detecting high-rate DDoS attacks, which are easy to detect due to the massive spoofed traffic against the SDN network. The evaluation of these approaches frequently employ unrealistic datasets that do not accurately present the characteristics of the SDN network architecture, since the structure of the SDN network is totally different from the traditional network. Some of these approaches exhibited inadequate performance when it comes to detect standard or conventional DDoS attacks. Moreover, none of the existing approaches attempts to detect low-rate DDoS flooding attack. So in this type of attacks, the attacker sent low-rate spoofed traffic, which is similar to regular traffic, since both having the same characteristics as legitimate traffic. Due to these difficulties, the existing approach is just concentrated on a standard or conventional DDoS flooding attacks and does not consider both simultaneously. Additionally, this table presents the SDN datasets that having some limitations Most of these datasets containing several traffic features, even though some contributed datasets having quite a few features. Most contributed datasets are limited to conventional DDoS attacks, except only these datasets. However, this dataset is limited only to UDP. DDoS attacks has limited traffic features and not publicly available. So this figure presents an overall methodology for the proposed SDN datasets and the deep MLB detection approach, which consists of 5 stages. The first stage is about generation and capturing stage, aims to propose a realistic SDN dataset. The second stage is about network traffic feature extractions, where a set of statistic features are deriving from the SDN network traffic flow. The third stage involves construction and pre-processing, preparing the datasets for the proposed detection approach to yielding meaningful results and significant results. The fourth stage involves dataset validation, conducted to ensure that the proposed dataset meets the requirement to serve as a benchmark dataset for this research and research community. The fifth stage is about deep learning MLB detection approach. It's training on the proposed datasets to enable effective detections of both high rate and low rate DDoS attacks. This figure illustrates the virtual testbed network topology for creating the proposed dataset, meaning it is considering to create a realistic virtual SDN network. The testbed feature a linear topology designing as the following: one OpenFlow one box controller acts as the root node and function as the network brain of the entire SDN network. One OpenFlow switches is acting as a gateway that connects the controller and the data link layer. The testbed consists of 64 nodes from 1 to 64. There are nodes act as attackers to generate high rate and low rate DDoS attacks against the SDN controller by targeting victim nodes. The remaining nodes generated normal traffic and act as a legitimate node. The proposed dataset considers 6 relevant scenarios. The reason behind that is to evaluate the effectiveness and consistency of the SDN security approaches in detecting 3 types of classes of DDoS attacks with different traffic variation rates. In this stage, the inbound and outbound network traffic are captured. The traffic is captured either from the SDN controller in the case of DDoS attacks or from the switches in the case of normal traffic. This step includes all SDN network traffic, both inbound and outbound. However, it's crucial to filter out relevant traffic to create datasets and save it as a backup file for further processing. This stage also involves transforming raw data into more suitable format. We utilize the CIC flow meter feature extraction method, recognizing for its ability to extract network traffic features. The output of this step, a collection of statistic feature extracting from the SDN network flows. Each feature carries a distance, meaning serving as an indicator of normal or abnormal flow. The reason or the rationale behind employing CIC flow meter is that it serves as a validated feature extraction method. It's used to extract different range of statistic features. Additionally, it's provide a more comprehensive and representative set of influential features. Also, finally, the dataset containing these features can be categorized as a flow-based dataset. The third stage involves construction and pre-processing the dataset by labeling, transforming, balancing to ensure equal distributed of label classes, normalizing the dataset features within a range 0 to 1. This step enhances the dataset quality and reliability and preparing it for the proposed detection approach to yielding meaningful and significant results. In this stage, the datasets undergo validations before being accessible to the research community. This stage aims to ensure that the generated datasets are applicable and fill all the requirements to serve as a benchmark dataset. These requirements including realistic traffic, diversity of DDoS attacks and scenarios, datasets completeness, labeling, sufficient traffic size, balancing traffic classes, representative features, and detection accuracy verification. This table provides an overall of the distributed of these dataset samples for both multi-class and binary class classification. At this stage, the dataset samples are applied to the proposed deep learning multi-layer perceptron detection approach. Two testing techniques are considered for assessing the detection approach generalization. First, the split test technique divided the dataset into sufficient large portions of datasets like 80 for training set to enable the model to learn diverse patterns, and 20 is reserved for testing set for evaluating the model performance on unseen dataset. The second is the cross-validation technique. This technique is critical for mid-evaluation as it involves training and testing on different subset of overall. Considering both techniques results in a more robustness approach performance assessment compared to solely relying on the split test technique. The following slide is about experiment results and discussion. This slide is about results and discussion. A realistic dataset has been generated to meet the requirement for serving as a benchmark dataset. Additionally, the proposed dataset underwent qualitative comparison with the existing SDN datasets and quantitative evaluation across all 8 scenarios to highlight its superiority. Based on the literature, these criteria has been formulated for qualitative comparison between the proposed dataset and the existing ones. So the candidated dataset must be realistic. Total number of instances up to 1 million. The dataset must include variety of attacks and scenarios. The dataset must be labeled, completed. The dataset must include sufficient number of features for allowing the researchers to understand more about the attacks patterns. The dataset must be verified in terms of detection accuracy. Finally, the dataset must be publicly available. As shown in this table, most of these datasets fails to include up to 1 million. Additionally, most of them fail to include both high rate and low rate DDoS attacks. The only exception dataset is this one. However, this dataset is limited only to UDP DDoS attacks and does not consider a variety of attacks. Some of the existing datasets are incomplete, having some columns are missing. Some of the datasets having insufficient number of features which are necessary for the researchers to understand more about the attacks patterns. Also, all the existing datasets have been verified at least in terms of detection accuracy, and most of them are publicly available. In summary, the proposed dataset addresses the limitation of the existing SDN datasets by considering a variety of attack scenarios. Also, the proposed datasets meets the requirement to serve as a benchmark datasets, include sufficient number of features. Overall, the proposed dataset is publicly available. The proposed detection approach also has been quantitatively evaluated using 8 scenarios as presented in this table. The comprehensive evaluations try to cover all possible attack scenarios, including both binary and multi-class classification. It includes evaluation metrics such as detection accuracy, precision scores, recalls for each individual classes. Based on the literature, these metrics are commonly used for evaluating individual classes. The finding in this table demonstrates that the proposed approach achieves good results across all attacks and scenarios. Moreover, the proposed approach has been quantitatively evaluated in terms of average performance. The proposed approach achieves high detection accuracy, precision, recalls. On the other hand, the proposed approach achieves low false positive, false negative, and true negative, while the classification error is minimum. These results observed from different type of DDoS attacks against the SDN controller. Conclusion, this paper introduces the HLD DDoS SDN datasets to address the key challenges in the SDN domain. This dataset simulates the prevalent DDoS flooding attacks with a variety traffic rates by meeting benchmark criteria for size, back diversity, and features. Also proposing anomaly-based detection approach for training and evaluating the datasets. The experiment results demonstrates that the detection approach exhibited good performance in detecting these attacks. For limitation, it's important to note that the proposed datasets were intentionally generated with a virtual SDN environment, addressing privacy concerns, enable control over the severity of DDoS attacks. However, this virtual setting may not fully capturing all network flows, such as variety traffic, network size, application types. The dataset scope is specifically related to TCP, UDP, ICMP, DDoS attacks. Also accommodating fluctuated in traffic rates. From practical perspectives, the proposed dataset serves as a control testing ground truth environment for the new SDN detection approaches. This approach allows for identifications of the strengths, weaknesses before implementation in a real-world network. So the proposed dataset stands as a valuable resource for the researchers, practitioners in the field of the SDN DDoS attacks. The future work, I focus on enhancing the detection approaches through the implementation of efficient sample feature selection technique. This approach aims to reduce the dataset dimensionality, ultimately boosting the performance and generalization of the detection approach. Also minimizing the false positive and classification error. This is the article source of the proposed dataset, validating the theoretical framework and methodologies employed in this benchmark dataset. For more details, you may